In this section, we are going to continue with sections 2.3 and 2.4, which are in regards to set theory, and we're going to start completing a few operations on sets. So we start with the definition, and our definition is the universal set establishes all who are available, which is often denoted by a U, and you'll see what that means with our first example. So our first example says, take set A, the letters in the name Savannah. What is set A? Well, A is equal to, it's going to be a set, so we use our curly brackets, and it's just all the letters in Savannah's name. So it's an S, an A, a V, an N, an H. No doubles because they would be redundant, and this is what we have. These are all of the letters in Savannah's name. So what would be the universal set here? Well, the universal set establishes all who are available. What are all the letters that could possibly have been in her name? So the universal set is just going to be the alphabet. The English alphabet, to be exact, in this case. So the universal set here is just the English alphabet. So the universal set is everything that's available, usually denoted by a U. So I could say U is equal to the alphabet. Another definition we need to start doing these operations is the complement. The complement of the set A, symbolized by A with little asterisk or A with little hat, is the set of elements in the universal set that are not in the set A. This idea can be expressed using the following set builder notation. The set builder notation is the complement of A is equal to X given that X is in the universal set and X is not in A. So if we go back up to our example, we have that the letters in the name Savannah are this set right here. The universal set is the whole alphabet. So what would the complement of A be? Well, in this case, the complement of A would be all the letters that are not in A, but are in the universal set. So they would be letters like A is included in Savannah's name, but B isn't. B, C, D, E, F, G, H is, but I isn't. A, B, C, D, E, F, G, H, I, J, K, L, M, N. N is in her name, but O isn't. And so on. You get the gist of it. All the letters besides the ones that are in the set. And that is how we define the complement. So we have an example here. Take a minute and see if you can figure it out on your own. We have that the set U is equal to all of the numbers from 1 to 10. Set A is equal to 1, 3, 4, and 7. So the complement of A is just going to be 2, 3, and 4 are taken, 5, 6, 7's taken, 8, 9, 10. It's just all the other elements, all of the other possible elements. Another example, let U, the universal set, be X such that X is a day of the week. Let A equal Y, given that Y is a day of the week ending in day. So, for example, A would be days like Monday, Tuesday, and all the other ones that end in day. So what would A complement be here? Well, there are 7 days of the week. There's Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. They all end in the word day. So the complement of A would be anything else, but there is not anything else. So we end up with the empty set. So the complement of a set that is equal to the universal set, if all of the elements are taken, the complement is just going to be the empty set. Cool. And now we'll define a couple operations. And these operations are a little straightforward, but they're a little weird to use, so we'll play with them just a bit. We have the intersection is the intersection of sets A and B, written as A with a big N, B, is the set of elements common to both sets A and B. This can be expressed using set builder notation as A intersect B is equal to x given that x is in A and x is in B. So for example, let's take the two sets here. A is equal to all of the x such that x is a letter in Dylan's name. And we'll take set B as all of the y given that y is a letter in Brian's name. And we want to find A intersect B. All of the letters such that that letter is in A, that letter is in Dylan's name, and that letter is in Brian's name. So the first letter I see that they have in common is a Y. I also see that they have the AN. And they don't have a D in common, they don't have an L in common, so that is it. So A intersect B is going to be just the set YAN. That is all the letters that Dylan and Brian have in common, that their names have in common. Notice we could also use, which we're going to talk about a lot more later on, we could use a Venn diagram notation, where this over here is set A, this over here is set B, and we have letters in Dylan's name are, well, letters in both of them are YAN. The other letters in Dylan's name are D, YAN, D, and L. The other letters in Brian's name are B and R. So we could also use Venn diagrams to show our information, to display our information. And we'll be talking about them more, so we'll do a few today. So let's learn our intersections by finding them. Find the intersection of the following two numbers, two sets. Take a minute, pause the video, and try it on your own. So the intersection of the first one, all the elements they have in common. I see that they don't have a 7 in common, but they do have an 8. I like to mark off the ones that I've used. They do not have a 9 in common, but they do have a 10 in common. And they do not have an 11 in common. So that is our intersection between those two sets. In number 2, they don't have a 1, they don't have a 3, they don't have a 5, they don't have a 7, and they don't have a 9 in common. So we end up with the empty set. We end up with two sets that have nothing in common, so their intersection is empty. Number 3 is a set intersect the empty set. Well, the only element they have in common is nothing, so they only have the empty set in common. So that is the intersection of those three problems. We could also do this, take a minute, we can also do this with a Venn diagram. For example, the first one, we'll just do the first one because it's the only one of note. We have 8 and 10 here. And then we have 7, 9, 11 here. We have 6 and 12 over here. And so with number 1, you immediately see, if you slowly go through each piece and decide which spot it should be in, you immediately see what their intersection is. Cool. Now we have another definition. The opposite of intersection almost, the other operation that we're going to be using, is union. The union of the sets A and B, written as A union B, AUB, is the set of elements that are members of set A or of set B or of both sets. This definition can be expressed in set builder notation in the following way. A union B is all the x given that x is in A or x is in B. And we'll use the same example as before. We'll use Brian's name and Dylan's name. So I have Brian and Dylan. In fact, I'll even write them like this with commas. These are my two sets that I'm going to be looking at. And I want to know the union of these two. So the union of them is going to include a B, it's going to include a D, it's going to include an R, a Y, an A, an N, and it's also going to include an L. The union of them is just going to be all of the letters given. Or if we are to do a Venn diagram, we have the same Venn diagram as before. They have Y, A, N in common. Brian has a B and an R. Dylan has a D and a Y. Oh, not a D and a Y. A D and an L. And in this case, my union is going to be everything in red. The union is everything that's in one, in the other, or in both. So it's the whole Venn diagram here is the union. And those are the two operations. So now let's do a couple union problems. 7, 8, 9, 10, 11. Union 6, 8, 10, 12 is just going to be, and take a minute and pause the video and try these on your own, but it's just going to be 6, 7. Notice 8 is here twice, but we're not going to double count it. We're just going to write it once. 9, same with 10, 11, 12. In the next problem, we have the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. So if we union them together, we're just going to have 1 through 9. I'll write it a little sloppy. And then in number 3, when we union something with the empty set, it means we're putting these elements together with these elements. Well, there are nothing here, so we just end up with 1, 3, 5, 7, 9. So the union of a set with the empty set ends up being itself. So now, let's do a couple challenging problems with everything we've learned. Given the universal set 1 through 10, we have an A and B set. Find, first, A union B complement. And we do this exactly how we would do regular math. So we see that we have A union B in parentheses. So let's do that first. Well, A union B, we'll find A union B is equal to 1, 3, 7, 8, 9, 10. A union B is everything in here, sitting next to everything in here. The complement of that, A union B complement, is going to be everything besides those numbers. So we have a 1, but we don't have a 2. We have a 3, but we don't have a 4, a 5, a 6, 7, 8, 9, 10. So that's it. So that would be A union B complement. It should be in parentheses, the opposite of that. Now, similarly, if we want, do this problem in a different color, if we want A intersect B complement, the first thing we need is A intersect B. We'll do what's in parentheses first. A intersect B, what do they have in common here? They have a 3 in common, and they have a 7 in common. A and B have a 3 and a 7 in common. So our complement of that is going to be the opposite of that, which is 1, 2, 3 is taken, 4, 5, 6, 7's taken, 8, 9, 10. And so now we have these other two problems. This time there are no parentheses. We have an A, we have a B, but we don't have A complement or B complement. So let's find them. And we'll put them right next to A and B. We'll say A complement is equal to, we have a 1, so we need a 2. We have a 3, we need a 4, 5, 6. We have a 7, we need an 8. Have a 9, need a 10. So that's A complement. Take a minute and try to find B complement on your own. B complement is everything that's not in B. 1, 2, 4, 5, 6, 7, 8, 9, 10. There we go. So we have A complement and B complement. Now we can find their union very easily. So A complement union B complement is going to be everything in both of those sets, which is 1, 2, 4, 5, 6, 8, 9, and 10. And A complement intersect B complement is everything that they have in common. So they have a 2 in common. They have a 4 in common. They have a 5 in common. And they have a 6 in common. Now notice our solution here for A complement intersect B complement is actually equal to A union B complement. And our answer here, change this to purple, to A complement union B complement is equal to, I should have an equal sign, A intersect B complement. So we have that two of these two here are equal to each other, and then these two here are equal to each other, which is interesting. And it's actually a rule that we learn. De Morgan's laws are that A union B complement is equal to, what you do is you distribute the complement to both pieces, just like if you were squaring something or if you were multiplying by something. The complement gets distributed and the sign gets flipped from a union to a complement. And similarly here, same exact rule, the complement gets distributed and we go from, oh, I called this a complement, sorry about that. We go from an intersection sign to a union sign. Over here we go from an intersection sign, from a union sign to an intersection sign. And those are De Morgan's laws. They were proven on the last slide using an example. So now this is just a quick set of problems. You can try them on your own, but we will do them now. A union B intersect C. So we follow the same rules of math. We say, what should we do first? Well, I see that this is in parentheses. And if I'm learning PEMDAS, I know parentheses is the first letter. So the first thing we'll look for is B intersect C. So what do B and C have in common? Well, they both have a 2, they both have a 3, they both have a 6, and that's it. 2, 3, 6. So A union that is going to be everything in A and everything here, which is just going to give me 1, 2, 3, 4, 5, 6. And if you haven't noticed by now, this stuff can be a little confusing if you don't do the practice problems. So I implore you to do all of the practice problems and make sure you are getting used to all of this notation. For the next problem, ACB, that's funny. A lot of mistakes in these slides. So for the next problem, we need B union C because we want to do what's in parentheses first. And B union C is going to be everything that's in B and everything that's in C. So we get 1, 2, 3, 4, 6, 7, 8. And that is B union C. And we're intersecting that with A. So we say everything that has in common with A. 1, 2, 3, 4, no 5, no 6, no 7, no 8. So that's everything that both this set and this set have in common. And now for the last problem, which I wrote as B for some reason, we need A union B, but we also need A union C. So A union B is 1, 2, 3, 4, 5, 6, 8. And A union C is 1, 2, 3, 4, 5, 6, 7. And we're intersecting those two sets. We're saying, what do they have in common? Well, they both have a 1, 2, 3, 4, 5, 6, 7. Not a 7. They don't have a 7 in common. 1, 2, 3, 4, 5, 6 is what they have in common. And so even though set notation, you don't really need to order things, it is good to order things or else you confuse yourself. And that is our new operations. The problems that you do in the future will definitely help you understand the operations. So we'll move on to what is the complement of the universal set? So if we have all of the elements, what's the complement of it? And the complement of the universal set, or everything besides everything, is the empty set. There's just nothing in there. And the opposite of nothing is everything. The complement of the empty set is the universal set. Now we have one more set of questions. What is something intersected with the empty set? Well, if you have something, it's not going to have anything in common with the empty set because the empty set doesn't have any elements. So this is just going to be the empty set. And similarly, if you have something, we're adding it to nothing. Something plus nothing is that same thing. So X union the empty set is just going to be X. And that is your new operations.